你是问他 converge 不 converge 还是
一个 value。
一个 value？你找 ratio 吗？那这是 geometry series。你确定要 converge 啊？你用 ratio test 不是？
因为 ratio test 找它 converge test 找它 converge 先。
他他答案啊，他答案一定要 converge 是不是？
对，
如果你不知道这个是什么，哦，你要找这个啊，还是你懂这个？
啊，我要找这个。
找这个。
对，
嗯，
诶，
嗯，
我说洗漱东西。
还有一个 P0的
可以大过0，
啊，
可以大过0.1。
要大过等于一吗？所以你可以放
嗯，
一进来吗？对，你可以放一进来吗？所以 P0是被 define 是吗？
啊，OK，
啊
我应该做错东西，我重新做个题。
，OK。 好了，
So someone suggests can you just
啊
do the continue the class on Friday. So we have your class then straightly go then you don't need to find another day to replace the class.
I can ask.
Uh,
Yeah.
mhm.
Are you like class rep for them or no?
That's
What
personal
you
suggestion.
personal
Personal.
or you got other suggestion?
No.
Just your suggestion.
Ah.
Oh. So you guys typically work like this or your own suggestion? Yeah, I'll ask them. It's before we start. Who is Hu Yuyan? Is Hu Yuyan here? Hu Yuyan. Not here. Hu Dongjie. Zhu Guling. Okay. Okay, maybe let's start. So good afternoon to everyone. I have received your assignment one. Yeah, started marking it. Yeah, I saw some of you making this collaboration statement. I think it's quite good. It's Pan Chi Feng. Pan Chi Fun. Pan Chi Fun. Wait, can I ask you where you get the cover letter? I mean, yeah, last is it online or previous student? Oh, okay. Maybe previous course. Can you send one copy to me? Because I don't know where to get them. I see that quite nice on cover letter. Also, I saw you guys using theorem from discrete math, right? Most of you. Maybe next time before you use it, right? Ask me first because no. The question is because maybe I want you to reprove that statement sometimes. Yeah, but you ask me if I say can use, then sure will use. Yeah, because sometimes I might ask you to prove similar stuff. Okay, so just ask me first before using theorem from other classes. But theorem from our classes, usually you can use it unless I state clearly I want you to reprove it or what. Yeah. Okay. Any result proven in this class you can use unless I really ask you to prove the exact same statement. Okay. Yeah. Usually you can use what we prove in the class. And then what else? Yeah, okay. So this Friday is a public holiday, right? I think you guys have heard it. So do you want to do want to do physical replacement or online replacement? Huh? Online? Online? You guys want to do online? Okay, let's see how many of you want to do online. For whoever want to do online, can you raise up your hand? We'll follow majority. Online. Okay. Wait. Keep your hand up first. But more of you want to do physical. More people want to do physical. So we follow majority, do physical. So the question is, when you guys are free to do physical replacement? Huh? Friday? Friday. Okay. So there's one suggestion say that we don't holiday, we do class, or you want to do on other Friday. Huh? So you guys want to come back this Friday? Is it? Is it? Okay, let's have a show of hands. Who want to come back this Friday? Not majority. So not this Friday. So which Friday you guys want? The following Friday? The following Friday? So let's say the following Friday we have class from 11 to 1, right? So you want to do it morning or morning? Okay, morning because usually this class we have a class before us, right? Unless we have to pick different time. So you guys want to do 4 hours marathon? Is it? No? Huh? No. So you guys want to have a rest. So you want to do 8 to 10 and then 11 to 1. Is it? What? But you say you want to do morning, right? But I want to rest. Yeah. Any suggestion? Okay, then I'm going to ask. Okay. What? May not what? You ask them to rest time or variable courses. They are not measurements. If you want to do, I mean, there's only two choices, only online or physical. If you don't raise them for online, must be physical. But I mean that means you forfeit your attendance, right? Oh, I mean, okay, one more time. If you can do online, raise on your hand. Okay, if you can do online, raise on your hand. If the choice is online, you accept, then you raise on your hand. Okay. Okay, so we'll do online. So when do you guys want to do online? When you get free? Friday same time. Or Friday same time. So this Friday again. Is it? This Friday same time online. Okay. So we just change the venue to home room, not at classroom. Is it? Okay. Okay. Sure. So decided this Friday, 2 o'clock on Teams. Is it? On Teams. 10 to 12? Okay, someone suggested 10 to 12. How about you guys? 10? Everyone okay? Any objection or not? No objection? So this Friday, 10 to 12 online. Okay, on Teams. I'll send out an link. Okay? Okay. Okay, so this Friday, 10 to 12. Okay. Yeah, so inform your friend who cannot make it today. And please don't sign for your friend. Please don't sign for your friend. Otherwise, I think it's very hard to control. Please don't sign for your friend. Okay, just sign for yourself. If your friend can't make it, just let them tell me themselves. Okay, yeah, don't sign for your friend. Another thing is okay, I don't care what you have experienced before, okay, and I don't know what you have experienced before. So for my class, okay, if you think that I'm too fast, if you think that I'm talking nonsense, or yeah, so please just let me know. Okay, just let me know. Okay, you can just straight away call up in the middle of the lecture. Okay, if you think that you need more example, you just call up. Okay, don't just think that you can go back and do revision. Okay, this method will last, but would not last for you until your future. Okay, because in future, when you talk to people, when you're meeting with people, you guys will be talking. I mean, you guys will be talk about new stuff. Okay, then you can't ignore people anymore because the new idea are coming from them. Okay, you cannot find it elsewhere. For now, you can do it because there's all around the place, the textbook, the knowledge. Okay, but future you can't. So try to make sense of what people are talking about. Okay, I know it's hard, but I provide a platform for you so you can ask me. Okay, it's not like I just ask you to understand it yourself. Okay, so please ask me. Okay, if you don't ask, you message me, email me, whatever. Okay, a lot of passages you can meet me. Does anyone get me? Okay, yeah. So just say, okay. Don't keep to yourself. Yeah. And yeah, okay, maybe we'll talk about other thing next time. So any question from last lecture or not? Last lecture. Just now I placed up this solution by Jiang Chen. So last time did we do this? I think we do this for, I forgot how we do this. Anyone remember? But we don't define a new geometric sequence. He construct a new geometric sequence out of this recursive sequence, and then he found that he found the limit of this new sequence, and then deduced the limit for the previous sequence. Okay, maybe you will ask a question: how they see this geometric sequence? I have no idea, but there's one point. I mean, yeah, it's about the theorem you learn in your discrete math. Right, if you have a recursive sequence, then you can somehow relate it to a root of some, you call it a characteristic polynomial. What do you call it? Characteristic equation, right? Anyone remember? I also don't remember. I just learned from some of you. Okay, so I mean, some of you use it in assignment 1 as well. Okay, so somehow there's a relation between geometric sequence and recursive sequence. Yeah, some particular type of recursive sequence. Somehow you can find a ratio between differences of terms. And it is not obvious, okay? I also don't know how. Seems like Ziqian is doing some research on it. Okay, so we'll wait for his project to see why is it true. So why given a recursive sequence, you will get a geometry sequence. Okay. Yeah. Any question? Yeah. Okay. Another thing is I think we like mathematics because it is like definite, right? If I give you a question, you must have an answer, okay? But most of the time when I say some theory in the class, I might not give the whole answer, okay? Maybe one, I don't want to give. Two, I don't know, okay? Yeah, maybe either I don't want to give, either I don't know, okay? So this happened in real life as well. So so you need to how to say, you need to get used to it. Okay. So for everything that you want to know, probably you need to find out yourself. Okay. Of course, now you have me here, so we can help each other. But in most of the case, you need to find out yourself. Yeah. Because when you work until new area or new field, right, you won't get help from anyone. Yeah. Yeah, so you need to get used to this kind of condition. Okay. Sometimes it needs a lot of theory to discuss, so we won't have time to do it. Okay. Do you get me or not? Seems like sometimes I say something too abstract. Okay. Okay, so last time we stopped at the Fourier series, right? Before that, we end at the infinite series, where we express function in terms of power of polynomials. Okay, in terms of polynomials. And in Fourier series, we want to express periodic function in terms of cosine and sine wave. Okay, cosine and sine function. And then we gave this formula here that day. Okay. When we write this in terms of cosine and sine, there's a coefficient in front of them. We call it an and bn. Okay. We even give the formula to compute this an, bn. So why is it true? This become a question in your assignment. Okay. So why is this true? Last time I gave a hint that you should use this special case. Okay, so you should use this special case and then try and prove that an is really that formula given. Is the formula given before. Okay, use this identity. Okay. Okay, and then next we stop at this theorem here. Okay, I feel like this theorem is not as detailed or as complete. So I extract another version of this theorem from Adam. Okay, so I extract this theorem from Adam. I'll replace it with this theorem here. Okay, so what does this theorem say? This theorem says that you start with a piecewise continuous periodic function. Okay, so piecewise, do you know what's piecewise? So you define by interval. Okay, maybe at different interval is different function, and it's continuous. Okay, it's periodic, and with. So you start with a piecewise continuous periodic function, and then this function has also piecewise continuous derivative. Okay, not necessarily periodic on f prime, just continuous piecewise. And then it says that the Fourier series of this function. So this means that Fourier series is kind of an operation. Okay, so you fit in a function, I give you the Fourier series of that function, right? Does it make sense? So you're handing me a function. Okay, if I do Fourier series, I found another function, right? So how to do that? So you hand me a function. Okay, you hand me a function. I do this integral to find the coefficient. Okay. So this is the This is how we find the Fourier series of a function. Okay, but why is there a S here? Why is there a S here? Anyone have any idea? You hand me a function, okay? I do Fourier series. I give you back another function, okay? So this function have to be defined on x as well, okay? That's why we got this little f and small x here, okay? Little f here means I do Fourier series on this little f, and then this function is applied on everywhere in the domain x, okay? Where does domains lie? This domains lie in R. Make sense? Any question from the back? I only see the front noting. How about side? Any question? The back? Any question? No? Okay. Okay. So we have this little f and x here. Denote that we got another function. Okay. We got another function. Okay. So next part is if f is discontinuous at one point, right? Okay. But Fourier series is always continuous. So this Fourier series will converge to the average of the left and the right limit of that f. Okay, so let me give you an example. So let's say so this example we will work out later, but I just give you context first. Okay, so let's say this is our f. Okay, so we approximate it using Fourier series. Okay, so you make up this curve, approximate this curve using some wave function. Okay, some wave function. But cos and sine is continuous, right? So there's no discontinuous point. Okay, but this function here is not that this point here jump, right? Okay, so this is not continuous because left and the right limit is different. Okay, but your first series is always continuous. Okay, no matter how close you approximate, right? Okay, it will have this vertical line. I mean, it's not a vertical line, but it's a slanted, almost vertical line. It cannot be vertical, right? Because if it is vertical, then it is not a function anymore. Right? Because given one point here, you have like multiple points. Okay, so it's impossible. You can only be as close to this vertical line as possible. Okay, so the theorem here says that the Fourier series is equal at this point. Okay, for example, this is the discontinuous point. Okay, this continuous. Okay, then this you can see that this first series cut at the point where you take the average of the left and the right limit. Okay, this is what this theorem trying to say. Okay, we will see it at the moment. Okay. First, we understand what this statement wants to say first. Okay. Any idea? Any question? Any question? So there are few objects here. Okay. So try to put 3 objects in your mind. So you have f. Okay. You have Fourier series of f. Okay. And then we are looking at the limit of c plus and c minus of fx. Sorry. X. Okay. Yeah. So when we talk about this, kind of theorem, right? Try to extract out what is the object first. Okay. So we start with a function. Okay. We start with a function. Okay, and then we do Fourier series of this function, we get another function, okay, Fourier series. And then we try to study the behavior of the original function when it's close to the point, when it is close to the point of, close to the discontinuity point, okay, or the point of discontinuity. Okay. So the statement is the Fourier series will converge to the point of the average of the right and the left limit of f. Make sense? Okay. Okay. So let's look at a real example. So we start over this example again. So we consider a function, okay? Start with a function where it is 0 for -1 to 0. Okay, x for x in between -1 and 0 is 0. And then it is 1 when x is in between 0 and 1. Okay. So in your mind, what should you think? So you should think of domain and codomain. Okay. So think of where the domain lies. Where the domain lies. So the domain start from -1 to 1. Okay. And then you cut this domain into two parts, starting from 0 to the right and starting to the left. Okay. And then f is 0. F is 0 when x is on the left of the interval. Okay, so let me go here. How about x on the right of 0? It is 1. Okay. So is this function periodic or not? Is this function periodic? No, right? Okay, so it's not periodic. But last time we studied that we can extend any function into a periodic function. How? We just repeat the pattern across the same length of interval. Okay. So in this case, what does it mean? We can do fx plus 2 equal to fx. Okay. Because the length of this interval is 2. The length of this interval is 2. So we repeat this over interval of 2. Okay. So we'll get a picture something like this. Okay. So every distance by 2 is the same point. Okay. Distance by 2 is the same point. Okay. Does it make sense up to now? Okay. Okay. So next part is then we proceed to find the Fourier series. Just apply the formula. Okay, just use the formula. So why is it true? I put it in as an assignment question. So we will use this formula here: A0, AN, and BN. Okay. So for example, A0 here says that you need to integrate your original function over the interval that you define the function. Okay. So where do we define the function over? -1 to 1. Okay. So we need to integrate this piecewise function. Okay. So we need to integrate this piecewise function here. So we will integrate from -1 to 0 and 0 to 1. Okay. And then divided by the radius of the interval. Okay. Where we get 1 in the end. A0 equal to 1. Similarly, we do it for AN and BN. So AN is the coefficient for the cosine wave. Okay. And BN is the coefficient for the sine wave. Okay. Any question? No. No. Okay, so we have done up to here last time. Okay, next we continue with this theory, this example. So next part is to what value does this Fourier series converge at x equal to 0, x equal to 1, and x equal to half. So let us bring this picture across. Okay. So what did we find last time? Okay, we find that we can approximate it using just sine wave. So you can imagine that we got this Fourier series looking like this. Okay. Okay. Makes sense. Okay. So the question is, what does this Fourier series converge at? F is s equal to 0, so which is this point here, and s equals to 1, which is this point, and s equals to half, so in the middle. Okay. So from first sight, what do you think? What does this Fourier series, meaning the purple one, okay, this purple graph, where does it converge to at x equals 0? Huh? Half, okay. How about when x equals to half? Maybe for the other to 1, okay. How about x equals to 1? Any idea from the rest? The other, or s equal to 1? Do you have any idea where this fx converge to? Fourier series. Into half. Okay. So let's check. Okay, let's check whether our prediction is correct or not. Okay. So what did we learn just now? Okay. What did we learn just now? We have the statement that the Fourier series. Okay, let's copy it down. This. So we have this. The theorem just now says that we have the Fourier series at that point, okay, is equal to the half or the average. Okay. So when we see this half, right, we should think of it as an average. Okay. Average of the limit coming from the right and left of the original limit. Okay. Original function, I mean. Right. Okay. So this question really is asking about f, little f on 0, f, little f on 1, f, little f on half. Okay. So applying this theorem here, we got that f little f of 0 is the average of the limit of x going to 0 from the left fx plus limit x from 0 from the right fx. Okay, which is what? Which is half of limit of 0 plus limit from the right of 1. Does it make sense? Does it make sense? Okay, because just now, remember, we start with the curve. We start with a curve. 0 on the left of 1 of 0, and then on the right of 0 is 1. Okay, so if you approach 0 from the left, you will meet this 0 part. If you approach 0 from the right, you will meet the 1. Okay, approach from the right. So what do you get? You get half time 0 plus 1, which is half. Okay? Make sense? Does it make sense? Does it make sense? Before making sense, right? If I say something nonsense, you should ask me again. Ask me to repeat. Okay? So first thing is you need to understand what I mean. You need to hear what I say first before you understand what I say. If I say something wrong, you should ask me again. Okay, so how about at 1? Okay, so we need to approach 1 from the right and approach 1 from the left. Okay, so you can see what happened when you approach 1 from the right and from the left. Okay, so maybe just look at this picture here. Note that you need to consider the original function, not the Fourier series, okay? So Fourier series is on the left-hand side. The original function is happen on the right-hand side, okay? So what happened at 1, okay? So if you approach 1 from the left, okay, for this function, where do you meet? Do you meet 0 first or you meet 1? Let me throw this away first. So if you approach 1 from the left, okay, which value you meet? 1, right? Okay, because it's a constant function 1. We don't note that we don't care anything here. Okay, you can see that anything on the left of 0 is sometimes 0, sometimes 1, sometimes 0, sometimes 1. But limit, we really care about the value that really close to 1. Okay, so we really care about only this part. Okay. Very close to 1. Okay, so it is always constant 1, so we put a 1 here. And then from the left, we get, when you approaching 1 from the left, you get 0. Okay, so in this case, we have half time 1 plus 0, which is half again. Okay, so similarly, you will do it for half. Okay, you can see that half is lying in the middle of fx equals 0, where fx equals 0. Sorry, fx equals to half. Maybe. Right. So if you approach the point x equals to half, fx is 1. Okay, no matter from left or right. Clear? Is it clear? So from left or right, it is just 1. Just half. Okay, so you got what? Sorry. Did I make a mistake? Okay, I want to correct my mistake. Did I make a mistake? Where did I make a mistake? Should be 1, right? Okay. The value is 1. So half times 1 plus 1, which is 1. Okay. So this theorem tells you that the behavior of your Fourier series at this 1, 0, 1, and half. Okay. So really, you can draw this curve out. Okay. So if you take more sine and cosine curve, you can see that these Fourier series will converge more. When I say converge more, meaning, for example, the slanted part will get closer to vertical line. Okay. Yeah, in later year course, you will learn different convergence to describe this behavior. Okay, different type of convergence. But for this course, we just learn how to compute Fourier series first. Okay. Okay, next. So by considering the value of the Fourier series at x equal to half, show that the following equalities. Okay, so this part D will show you how useful is Fourier series. Okay, so we can find some expression for irrational number. Okay, pi is an irrational number. Previously we have this Fourier series. So let us bring this down here. Okay. Paste. Okay, so we want to check this Fourier. It says that check this value of Fourier series at x equals to 1, right? So we just plug x equals to 1. Sorry, half. Let's do ff on half. Okay, what do we get? We get half plus the sum of n equals 0 to infinity times this coefficient we found last time, multiplied by n pi over half over 2. Okay. Okay, so is this helpful or not? This helpful? What else can we do? How to find the pi out? How to get the pi out? This. Any idea? So we already did what the question want us to evaluate, right? So what's this equation here? What have we done in part C? What have we done in part C? I don't want you to answer. Sorry. How about the rest? What have we done in part C? Huh? 1. Okay. So from part C, we know that ff half is equal to 1. Okay. What's next? What can we do? Huh? Subtracting half? Sure. We can do that. So how do we deal with this infinite series here? How do we deal with this infinite series here? Do we deal with infinite series here? Let me start with the wrong. How do we deal with the infinite series? I think there's only one way. There's only one way, I think. Any idea? Huh? Rich. No, I mean, our goal is this, right? So you need to somehow come up with these pi and then these terms. So how to come up with these terms? change it to alternating? Why? What do you mean by change it to alternating? What do you mean by that? No, I don't understand. I just want to ask. What do you mean by change to alternating? What? Say again. Using a Fourier sine, then you can get the alternating. Okay, so you mean evaluate this, you get 1 minus 1, 1 minus 1, 1 minus 1, something like this. Okay, yeah. So we just evaluate. You evaluate it. Okay, yeah. We just evaluate this sine n pi over 2. Okay, so why sine n pi over 2 is alternating? Continue. I draw continue. Okay, so meaning you look at the sine curve, right? Then you look at the sine curve, pi, 0. Okay, so what happened at the interval of half pi? Okay. So you got pi over 2, 3 pi over 2, again, then keep going on. So you can see that at pi over 2, 3 pi over 2, and then 5 pi over 2 alternating between -1 and 1. But how about at pi, 2 pi, at a whole number of pi, what happened? It's just 0. Okay. So what do we get? So let us write down. We start with n equals to 1. So for this infinite series, right, you really should do it term by term, slowly, when you start at first. So you just put this when n equals to 1, what happened? And then when n equals to 2, what happened? And then when n equals to 3, what happened? And then slowly, when you put a few more terms, you will see what is going on. Okay. So let us do until the third term. Let's do until the third term. Okay, so what do we got? What do we have for the first one? So we have 2 over pi on the coefficient, and then sine of pi over 2. And then for the second term, we say that at whole number of pi, it gets to 0. We don't even need to care what happens here. Okay, so this term goes to 0. Plus 0. And then plus the next one is to the power 3. So you can see that the odd number terms here save this coefficient, right? When it is odd, this -1 is minus, or minus become plus. So I save it, become 2. 2 over 3 pi sine 3 pi over 2. And then you can see that the pattern is like going on. Maybe here is a 3 over 5 pi sine pi over 2. Okay, so when I write this down, right, it's not trivial, but you need to write out. Okay, I just deduce for you. Okay, then you can keep going. Did we do something wrong with sine or not? I think there's a mistake here. Can anyone find a mistake? Anyone find a mistake? In the last row, there's a sign problem. There's a sign problem. See it? There's a sign problem in the last row. Huh? Any idea? Oh, not yet. Oh, not yet. So not yet. Just trying to trick you. Next. What do? We just evaluate the sine function. Okay. So sine pi over 2 is 1. And then sine 3 pi over 2 is -1 plus 2 over 5 pi times 1 and then so on. Okay. All right. So it's equal to 1 on the left-hand side. So you can see that there's always a 2 at the numerator, right? On the right-hand side, and always a pi in the denominator of the right-hand side. So you can divide and multiply by what? So you can do pi over 2 equals to 1 plus, sorry, here become minus 1/3, and then plus 1/5, and then so on. Wait, let me complete this line first and then see what's going on. Okay, so what's going on here? The question asks about pi over 4, but we get pi over 2. Yep. Huh? Huh? My 1 is 1. Say again. Say again. Last second. Also, you want the 2. Okay, yeah, correct. Okay, good. So here is pi over 2 times pi over 2. So we got pi over 4. Okay. Yeah. Yeah. So let's see. Okay. Yeah, any questions up to now? No. Yeah, there's one thing I want to share. So there's one thing I want to share. So when I first studied the math course, right? Okay. I also blank out. I mean, blank out after, for example, first year, I will blank out. Surely I blank out after 50 minutes. Okay, after 15 minutes, I confuse. And then second year, I get better. I blank out after 30 minutes. After 30 minutes, surely I get confused on. I don't know why. Like the time tick until the 30 second, I sure confused on. And then the third year, I confused after 45 minutes. Okay, getting better. So, I mean, I think it's kind of natural. Okay, kind of natural. But slowly I get that why I confuse. Okay. So, I mean, I'm not sure. Maybe it's the way we learn it. I mean, I'm not sure about you, at least me. Okay. So we tend to like take in everything what teacher said. Okay. Let me ask you a question. When you are full, okay, you eat. When you're full, what do you feel? What do you feel after you eat? You are full. What do you feel? Do you feel anything like if you eat until very full, too full already? What do you feel? Sleepy. Right, sleepy. You just take in what the teacher said, the lecturer said. Of course you're sleepy, right? Because you are too full already. So what you need to do? You need to digest. Okay, you need to digest what the lecturer said. Okay, you need to digest what the lecturer said. So part of the digestion is you ask if you don't understand. You don't just take everything in. Okay. Okay. So you need to digest what people say. Okay. So you need to differentiate what I say. Sometimes what I say is everything. I mean, is full theory. Sometimes what I say is a half theory. Okay. So you need to differentiate what I say. And then sometimes what I say is wrong. So you need to differentiate. Okay. So you differentiate what I say. Okay. If sometimes I say something that not full. Okay. I mean miss out some part. So you need to differentiate what I say every time. Okay, so don't just take anything what I said is true. Okay, otherwise you will confuse. Yeah, that's what I thought. Yeah. Is it clear? Okay, I mean, maybe this is a new stuff for you, so you should practice, keep practicing, keep practicing. Okay. And then the one good thing I can tell you that is once you master this skill, right, you can survive in any field, and literally any field, not just mathematics, any field that you don't know. Oh, like yeah. Okay, yeah, that's what I want to say. Some advice for you. Maybe you complain some lecture not good, that not good, this not good. I also make that kind of lecture before. Yeah, only do proof, and then in the tutorial we do exercises. Yeah, something like that. I mean, yeah. So we have to like go through it. I mean, yeah, you cannot avoid. So you cannot just always stay at your comfort zone. I mean, people like to stay in their comfort zone. It's comfort. You don't need to change. People change for you. So this is a part of growing up. Oh, you should. And try to learn whatever you can learn now. Because after you go and work, I think you could hardly learn. You have more time. I'm not saying that you cannot learn, but it's harder. So if you can learn whatever you can now. Yeah. Okay. So let's take a break until 3:08. We'll continue.
明修明修没有人。捐学，OK 啊？什么？忘记了有课，OK。去救人，救人重要。
他说如果上班做作业的时候，这么个问题就是，我这个化解的过程，我感觉没有问题，但是我就是跟答案是差的。
很圆。哪一个是答案？这个是答案，这个是你做的。
上面是答案，这个是我做的。
是换那个你没有抄他的 index 出来。index
啊，对，我忘抄了，但是
他可能只是换 index 呢。
他没换，他也是啊，这下面啥
一模一样。
一模一样。那我还有这个，还有下面。
哇，很复杂哦，很复杂，越来越复杂了。等一下我看一下啊，你有没有比较快？
我只想问一下
，OK
这个 setting 到底是什么意思？这两个
OK，回答这个先。等一下我看，如果来不及的话，你发给我。OK，等一下帮你看一下。是哪一两个？这一个跟这个还是？
前两个。
啊，两句话就是你给我比。说这个句子应该要这么猜。这个东西 converge to 这个东西。Okay，所以是 Fourier series converge to a function at every point. It's continuous. OK，然后 Fourier series of 什么东西呢 ？of 一个 piecewise continuous，不是任意的 function 啊，一定要 periodic continuous piecewise 不止，还要有 piecewise continuous derivative。
为什么这个
什么
piecewise continuous derivative 这么重要？为什么这导会这么重要？
这你就要看它的证明。对，因为取这些 limit 的时候，就可能会涉及到这个 derivative。因为你记得 derivative 是这个吗？ 加了一些这种东西，对不对？对吧？跟这个有关系。我怎么讲呢？这样，如果要仔细一点就要看，因为我们应该不会用到。好吗 ？OK，
上网找一证，
什么？
如果上网自己找一证，对，
哎，他说要去找一些这样的书，上网找的，上网找的，你要搜世界首富。我觉得你刚才就要问这个问题啊。我觉得你的同学也会有一样的问题，
确实这两句话
太长。我看一下这在干嘛？
然后
Yeah
还有一个很奇怪的，就是这个的话也是同样出现了同样的问题，就是它的答案是这个，但这里是加，这里是加不是减，它的答案是这个，但是我画出来是这个，但是呢，它下面有一道题跟这个是一样的，只不过上面不是一是 x 的方，但是用 x 方那个画出来的话，这个答案就是对的。就是它相当于，因为它这个上面多出一个 x 方的做法，不就是把 x 方提出来，然后再进行一个这个对，然后做成这样子，再把 x 方乘回来嘛。但是它上面 x 方的那道题，它这个答案就是这个，但是不是上面只有一的那个答案，它也是这个。
OK，你可以把这些东西写大一点，写清楚一点，然后再给我看一下，对比一下。对，包括这个 index 全部把它写出来，因为这个东西对于这个 index 很重要，index 一变啊，这东西会变的，
对啊，
所以 index 很重要。所以
我知道，所以我知道很多人，因为我
但是看起来你步骤没有什么错，只是不是你的 index 中出错了？有时候呀，诶，你看你为什么忽然间这边加？
因为他是前面提了
哦，对，OK，可以的。不懂，我觉得你要写出来一些。
那个教科书上只有答案，他也没过程。
对，
很折磨，就算完之后
应该版本是对的，对不对？
版本
是对的。
我就用的是老师你发的那个教科书，
啊
同个书后面的答案。
可以。我觉得你写清楚一下给我看一下，我感觉你步骤对，但是我现在也是看不出来干嘛。呀，
那天坐在这耗了好久，
你写清楚来发给我，发给我 P， 也可以发给我 email 都可以。
Yep, will also be on the test run. Include.
Yeah, I think so. Yeah, I think so.
Okay. And then for the one that you mentioned, using discrete and button, Is it like only Zhejian or some students? Because I don't know what.
Oh,
You said that some students for the assignment they use like something from this group. Like which question is it?
oh, first question. Before they figure out the Fibonacci formula using the, because in discrete math you guys did something relating recursive sequence to roots of characteristic equation. So they use that to solve it. But yeah, they use it. Why?
I forgot how I did number 1.
Oh, okay. That's fine. That's fine. I mean, yeah. Just that I want them to be aware that let me know before you use theorem from other places. Hello? Okay. So
I've been a bit lenient on this attendance list, so I want you guys to be responsible for your own attendance. So please don't sign for the one that don't come today. Okay. Ask them to speak to me. Okay. So if they want to be absent, it's fine. It's their business. So they have to deal with it themselves. Okay. So yeah. So I hope you guys are grow up person. So. Yeah. So ask your friend to talk to me. Yeah. Please don't sign for them. And what else I want to say? Okay, so I still want to emphasize, I don't really care about what method you use, okay? And don't ask me about any correct method to use, okay? What I care is your argument, okay? Your argument. So why is it true? Okay. So focus on argument instead of just method solving. Otherwise, you will be no different from the other math student. I mean, not from MAT. I mean, other degree also doing math, right? Okay, so they're also doing this syllabus. So what's the difference between you and them? Okay, let's say you just know how to calculate. You are math degree. They are maybe engineer, AIT. They know computer. They know AI. They go engineer, but you only know how to do maths. So what's your strength? Let me ask you, what's your strength? Right? So now I'm teaching you another strength, okay? Understand abstract idea, okay? If you wish to learn, you with this strength, you can master their knowledge, okay? This is what I want to convey. I'm not sure whether I will meet you in future or not. So maybe I treat this as the last chance, okay? So I'm trying to tell you what I learned from my math degree. Yeah. Okay. So toward the end of this lecture, I hope you guys can understand abstract idea that other people are talking about. Okay, maybe it's too ambitious, I don't know, but let's see how it goes. So we are all experimenting. Okay. I mean, along the time, I will adjust the difficulty of this assessment because I'm also first time teaching. So I will depend on the result, I will adjust the difficulty. So don't be too worried. Okay. You don't worry, you'll get 2 low marks or what. Don't be worried. I mean, this mark will be adjusted if it is too low or what. Okay. So you don't no need to be worried. Just do your best. Okay. Do your best to learn, do your best to achieve your best result. That's all you need to do. Okay. Don't need to worry about your result. Okay. Just do your best. Okay. If you want to get good result, do your best. Definitely. Okay. Yep. Okay, finish talking about other stuff. So just now we find this Fourier series of the piecewise continuous function. Okay, so what this you can use this online tool. Okay, I put the link in the Moodle as well. If you want, you can search for this Fourier series of grapher also can. So next time, if you want to see what does the Fourier series look like, you can put this in. You can put this formula in, but you cannot shift by half as the formula suggested, but you just shift by yourself the graph produced by the online software tool. Okay. So if we try to graph out what we have just now, that question. So if you graph up to the number 5th term, you will see something like this. Okay. Okay, I finally found what's the terminology for this. The top part of the wave is called crest. Yeah, I forgot last time. It's called crest. So you can see that the crest increasing, the number of crests increasing when you increase the number of wave. Okay. So you can see that although the number of crests increasing, right? Like what I said just last time. Okay. So when you go, I mean, if you have a lot of these crests, actually you don't really recognize the crest anymore. It's like a dot. Okay, it's like dot. The idea is like dot. So if you have few dots, you can recognize there's a distance between the dots. Okay, if you put more dots and more dots between the dots, what you get in the end is really a line. Okay? Yeah, this is the construction of a real number. Okay, you look at the limit of this dot, and then you fill in the dot, which we call the irrational. So we fill the line with rational, and then we fill the whole with irrational, and then we get a whole real line. Okay. Hey, by the way, speaking about project, how many of you talk with me about project already? Can I see the rest of them? How many of you talk about your project with me already? You and right. Who else? 3. Who else talk about 4? Yeah. 之前 also, right? So for those who already talk about your project with me, right? Can you send me the topic? I mean, not the exact topic first, just the content. Yeah. I mean, final title you still can change, but send me the content first. I want to list them out. Okay. Yeah. Okay. Is it okay or not? Understand or not? Actually, I sent an email already. I'm not sure you guys received it or not. Or read it or not. Please do. Okay. Okay. Yeah, for the rest, if you're still thinking about it, you can come and talk with me. Okay, so you can see that when you do until the 500 term, it is close to the function we started. But not that this is not the original function, right? Original function doesn't have this vertical line here. Okay, this is a bit different from the original function. Okay, so this diagram may be also not really accurate. Okay, so if you zoom in further and further, right? So you should see a bit slender, a bit slender, a bit slender, a bit slender. Okay, you can never see vertical line one. Otherwise, you won't get it is not a function. You know what I mean? So on a single point, you cannot have multiple f. Okay, so if you go deeper and deeper and deeper, you still can see a bit slender, but you can never go vertical. Okay, makes sense? Yeah, so this is a bit inaccurate, but it's an approximation. Okay. Yeah. Okay, next. Next we'll split our function into even and odd. Last time we already mentioned about this idea. So what's an even function? So an even function on an interval if and only if f minus x is equal to fx. Okay. So what does this mean? So another categorification characteristic of this function is, so this is definition. So let me put here definition. Second is property. So second property is if you integrate along this interval where it is even, you can split the interval into half. Okay, you can split the interval into half, and then integrate over one interval and then multiply by 2. Okay, this also characterizes this even function. Okay, so this is an example of an even function here. Okay. So yeah, so you can see that fx, okay, fx, x is here minus x is here. Their f value is the same. Okay, make sense? Yeah. Okay, so next, odd function. So what's odd function? So odd function is fx x minus x equals to minus fx. Okay, so example is what? Example is the sine function. Okay, so sine function, you can see that when x, so for example, let me go the example. So you can see that the sine x here. Okay, so when x equals to pi over 2, it is just 1. But when it is at minus pi over 2, you get minus 1. Okay, so this is odd function. So what's the property of odd function? So the property of odd function is the area will cancel out. So if you integrate along this interval where it is odd, you can see that the integral is 0. Okay, so the integral is 0. Yeah, this finding area, we will meet it again afterward. So the positive part is positive, and then the one below the x-axis will be negative. Okay. And then they cancel out when you add them together. So one thing I want to add here is when you find this area, right? There's really something to do with the orientation of this curve with the axis, with the orientation of the x-axis. We'll talk about this a little bit more later. Okay. Yeah. Yeah, for something, and you just need to believe me first because I haven't tell you yet. Yeah, so you just listen it as a story. Okay. Yeah. Sometimes you listen it as a story, sometimes you listen it as a fact. So you need to differentiate between I am telling a fact or I'm telling a story. Okay. Yeah. So because we don't have enough tool yet, so later when we have tool, then we will talk about it more. Okay. But for the moment, the key point is, so you can pick the key point of this slide. So the key point of this slide is you need to know the definition of even and then the definition of odd function, okay? And then the property of even and odd function when you integrate over the interval, okay? So this is the key point you need to know from this slide, okay? Is it clear? Remember that last time we said that odd even function can be approximated by just cos or cosine, cosine or sine wave, or even function. Any idea? For even function, we can just approximate by cosine or sine function. Sine is odd, right? So even should be approximated by cosine. Okay. Sine functions, even function approximated by cos even function, and then odd function approximated by odd function. Okay, we will see this as a theorem. Actually, it's a theorem. Okay, so I don't know about you, but for me, it's like I will feel a bit itchy because you tell me something is true, but you don't want to prove to me what it is true. Okay, but this will be always practiced in this class because we are not into the pure theory yet, so we're just using it. So if you are really interested, you can read about it. But if you don't understand, you can come to me. Okay, so this is the remedy. Okay, because we are going to use a lot of theorem. Okay, if I'm going to teach theorem, then there's no time for calculation. So you have to pick and choose. Kind of pick and choose. Okay. Okay. So the theorem is, I already stated last time. So if fx is an even function on an interval, okay, and bn equals 0, okay, then its Fourier series is given by approximating the function by cos function. Okay, so there's an extra condition here, actually. So when bn equals 0, so meaning the coefficient of xn is equal to 0. But why is this a theorem? I don't know. Let's see. So we also have the odd function theorem. Okay, so if the function is an odd function, okay, a0 is 0, an is 0, so meaning all the coefficient in front of the cos is 0, then you can find the Fourier series is equal to the linear combination of sine wave. Let's see how this works. So for example, consider this function here. Okay, so just consider this function, fx equal to x squared. Picking the interval between minus pi to pi. Okay. Does anyone know or not know how to plot fx equal to x squared? Does everyone know how to plot x squared? Okay, so let me briefly do this. So what's the basic curve for fx equal to x squared? Is this a parabola, right? And then we restrict this parabola to minus pi to pi. Okay, so meaning we stop at pi squared, right? Okay, so this is not periodic, right? But we can make it periodic, right? So we repeat every 2 pi interval. Is it true? All right. Okay. So we make it repeat at 2 pi interval. So which is we made that fx plus 2 pi is equal to fx. So let's say we want to plot the graph from minus 3 pi to 3 pi. So from minus pi to pi, we have this basic graph. And then over a different 2 pi interval, we will repeat the basic curve again. Okay, so if you go beyond 3 pi to 5 pi or minus 5 pi and then keep going, you can keep going. Okay. Now it is a periodic graph. Okay. Now it's a periodic graph. So now you can find the Fourier series of this function. Okay, so this function is even or odd? Is this function even or odd? Okay, let's recall what's the definition of even function. So even function is a function that is satisfied fx equals to f minus x for all x. Okay, maybe in R. And then odd function is fx equal to minus fx. Do we have another? I think we have another minus x inside for all x in R. Okay. But blur everything. Okay. Much information. Yeah, I think 3 hours for a maths class, I think too long. I usually only have 1 hour lecture every day. But I don't know how these school arrange it. So they want to train you become a soldier. My soldier. Yeah. So yeah. Maybe in future we can change it, but not now. No. Okay. So yeah. Okay. So please wake yourself up. So now it's an even function or odd function in this case. Okay. How to check? How to check? How to check? Hey, good idea. Good idea. Okay. So you see, the key point here is this f minus x. Okay. Fx is given. Okay. Fx is given already. But the point here is I don't know what is f minus x. Okay. So we sub f minus x into this function. Okay. Consider f minus x. Okay. Consider f minus x. So our fx is x squared, which is minus x to the square, which is just x squared. Okay. So x squared we return to the original f, which is f minus x equal to fx. So this is a even function. Okay. So for even function, so let me write down first. So we see that things f minus x equal to x squared equal to fx. Okay. Fx is an even function. Okay. So if it's an even function, then Bn is 0. Okay. Bn 0. Then An is equal to, what's the formula of An? Sorry, should we do A0 first? Okay, let's list out the both of them. Let's list the formula down. So A0 is the constant term, which is what? Which is what? Anyone can remember what's the formula? 2 over L integrate from a negative L to L fx dx. Okay. An is the same but multiplied by cos n pi x. Am I right? Yeah, I think I'm right. Okay, so what's our L in this case? What's the L in this case? Pi, right? So our x is in between what? Minus pi to pi. Okay. So our L is pi. Does anyone not agree? L is pi. Does everyone agree? Okay. Yes. So our fx is x squared. So we're gonna integrate this guy. So what's this? This is just s cubed over 3. Evaluate from Am I doing something wrong again? Did I do something wrong? Huh? Okay. Why? Can you tell us? Okay, this is written from the theorem before. Good, very good. Okay, so this is written as the theorem before. So we have to start from 0. So there's a difference between just computing first series and first series of even and odd. Okay, so from even, we integrate from 0 to L. From odd, we also integrate from 0 to L. Okay, so let's remove these. Maybe you can experience with minus L and then see what's happening. I think they will cancel. You can try yourself. Okay, so what's this? What's this? This is just 2 pi square over 3. Okay. Okay, next, let's compute this. I'm a bit reluctant to compute these things. So to compute these, you need to use by part, I think. Use by part. By part. Do you have to by part yourself? Can you guys by part yourself? So we just give you the final answer. To be pi, let me see, n squared. Or you guys want to see the by part? Anyone want to see the by part? Do you want to see the by part or you want to see the by part? Huh? You want to see? Okay. Good. Let's do it. Okay, let's do it. So how to by part? Let's show this by part. Operation by part. So let u equal to x squared, dv equal to cos n pi x dx. Okay, and then du is equal to 2x dx. Then v is equal to sine n, yeah, nx over x over n. Yep. N pi x. I mean this pi, is it? Let me see. Let me check. Let me think. Huh? What? You agree? So why? Tell us why. Already have pi, you mean? So what's the reason? Cancel. Okay. So I think I forget to substitute the pi, is it? Forget to substitute the pi. So we left with n pi. Yeah. So this one becomes this. Pi and pi cancel, right? Yeah. Okay, good. Okay. So next, what do we do for integration by part? Maybe let's just start a new page. Okay. So let's start a new page. So I'll click away this. Okay. So integration by part, uv minus integrate v du, right? V du. So you get sine nx over n times du, which is 2x dx. Okay. So you keep going. So you keep going with the by part. So you sub u equals to x, and then dv equals to sine, right? Next, dx. So du equals to dx, v equals to minus cos nx over n. Okay. Yeah, so we keep doing by part until we get back the same term, similar term from what we started from. So in the end, what do we get? We get minus uv, so minus minus become plus, so sine cos nx over n. Okay, and then minus v du. Okay, so minus minus become plus again. Okay, cos n dx. Okay, we don't get the original term, but we can keep going on. So keep going on. We get integrate cos x, we get sine nx over n squared, is it? Plus c maybe. Okay. Any problem with this? Yeah. Why I choose x? Okay, let's see. We can experiment with this. So you mean you want to pick u equals to sine nx? What? Why I don't want to pick the 2x? Because I can just pull it out. So I forget my 2, is it? I can just pull this 2 out. So I think I forget my 2. So I can just multiply by 2. Multiply by 2. You can use 2x, it's the same. So the 2 still stuck with it. Or you can pull the 2 out first and then do the integral. Yeah, it's the same. It's the same. Scalar doesn't affect much. Yeah. Okay. Is this correct or not? I don't have answer. I just do it on the spot. Okay. Any? Okay. No objection. So we need to evaluate this from 0 to pi. So we need to evaluate this from 0 to pi. You want to do this or you want to skip this? So I need to evaluate this from 0 to pi. Okay. Okay. Any question so far? So I leave it for you to evaluate. Is it okay? Okay. 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 So yeah. So what's the final answer again? We get -1 alternating multiplied by 4 over n squared. So yeah, write our Fourier series as f equals to a0 over 2 plus the sum of n equals to 1 to infinity minus 1 to the power n 4 over n squared cos n pi. Okay, so the sine part disappeared. Okay, how about next? So next, so considering the value of the Fourier series at x equals 0 and x equals pi, show that the two equation hold. Okay, so we come back again with this application of Fourier series. So I need to evaluate
the Fourier series we find at a right point. I will just put F here. And let's put it back. Paste. Right. Here. So I think I put some wrong indexes. Okay, so let's see what we have. So we need to evaluate the function at x equals 0. So at f equals 0, what do you get? What do you get? Let us also bring the original function back also. Let's bring this original function back. Okay, so just now we said that this value is the average of the right and left approaching f, right? Okay. So you need to approach 0 from the right and left, and then take the average. So we approach the function from the right. So let me write out what I say. So you need to take the average of the limit from 0 from the left of fx plus the limit of x 0 plus of fx. Okay. So if you want to approach 0 from the left and right, okay, so what point do you reach? 0. Okay, so it's half times 0 plus 0, which is just 0. Okay, we know that Fourier series at 0 is of f at 0 is 0. So how about the right hand side? How about the right hand side? Right hand side. How about right hand side? Hey, have we found A0? Huh? We have found A0, which is pi square over 3. Let me replace this A0 first. Pi square, pi cube, right? Pi square over 3. Okay. Pi square over 3. So here is a pi square over 3. Okay, so what's the right hand side of this thing? Cos 0 is what? It's just 1. Okay. So we just have the sum of the coefficient. Right? Yeah, so what's the sum of coefficient here? So it's 0 equals to pi square over 3. What's this sum here? So when n equals to 1, you get -1. And then 1 square is 1. So you get -4. 2, you get plus 4 over 4. And then minus 3, 4 over 9. And then what do you get? Plus 4 over 16, right? And then keep going. Okay, so kind of horrible. Let's see what's going on. So we want pi on one side, right? So let's move pi on to one side. And then we swap all the sign, right? Because move all to the other side. Okay, then we see that the 4 is repeating, so maybe it's helpful to do it. Move it. Actually, we need to do based on what we want, but I'm just trying to play around with it first. And then see, is it what we want? So one of them is pi square over 12 equals to 1 minus
2 squared plus 1 over 3 squared minus 1 over 4 squared. Okay, so this is what we have here, right? Okay, so how about the other one? How about the other one? The other one we need to do at another point. So let's just keep going. So keep going. So we still have another point to show, which is x equal to pi. Okay, x equal to pi. So when x equal to pi, what is it? So what is f pi? ff pi. What is ff pi? Okay, so if you approach pi from the left and from the right, what do you get? Pi square, good. So you get pi square. Pi square, which is 2 pi square, right? Over 2, which is pi square. Okay. And then what do you do? Then you need to substitute your formula when x equals to pi. 1 to n 4 over n squared. So what is the formula? Cos n pi. Cos n pi. Cos n pi. Cos n pi a bit troublesome, right? Is it troublesome? Because you alternate between +1 and -1. Okay. So you alternate between +1 and -1. So how does it alternating? So let's just write down. So cos n pi is -1 to the n. Is that true? So when it is 0, it is 1. When it is 1, when it is pi, it is -1. When it is 2 pi, it is 1. Okay, so it's -1 to the n. Okay, so -1 to the n times -1 to the n, you get 1. So you cancel out the alternating sign. You get sum of 4 over n squared. Okay, so what's next? Next, you just move pi across. You will get 2 pi squared over 3 equals to sum of n equals 0 over 4 over n squared. Okay, I believe we want pi squared over 6. So we can move 4 across. Right, so divide by 4, which we get pi squared over 6, sum of n equals 0 to infinity of 1 over n squared. Okay, which is what? Wow, this one a bit weird. We start with 0. We start with 1 or 0? 1, right? Okay. Otherwise, we will go into trouble. So be careful with this indexing. So when you write down, make sure it's the right index. Okay, so in this case, we have sum of 1 over squared, so 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, and so on. Okay, so is this what we want? Okay, so this is what we want. So as desired. Okay, so yeah. So you might see that this Fourier series may be quite daunting at first, but if you evaluate at certain point, maybe it comes up with nice result. This is one way to find the sum of the convergence series. Okay, maybe you can show these series converge, but what does it converge to? Okay, we don't have a general method to solve it. If it appears to be some value evaluated by the Fourier series, then maybe you can find the sum. Okay, this is one way to get it. Otherwise, you can use the power series as well, right? series. When you expand tangent x, when you expand ex, e to the power x, when you expand 1 over 1 minus x, okay? Right? Yeah. Okay. Like the infinite series is something you want it to converge, and then the function you can just evaluate it, and then you get the point out. Okay, the fx. Okay. So any question? Any question? No? Maybe we take a break until 4:02 and then continue. Is the attendance list done already? Can you pass it to me? Thank you. Cho 怎么样？
那咋了？
可是你怎么搞一个临界的，是一个需要满足完成用量的基本都少。卡的地方是，卡的地方是因为你的那个就是习惯风格怎么样？所以说，你如果要加这个调大约。
这种偏把这种跳的我个人的。这种看似现实怎么在觉得然后会让你出错，不要是变等什么？我这个第二个。第三是不是哪一个真的？要符合你看，我也都是这个的话，你就要在获取。那么传统从你的发现它分出了两个重点，然后那个共同点如果是对的话，就是点来。等的话，你还要再去看一下有没有。如果最常见的，然后说，最容易出问题的就是把那个加几倍，确实。单点分割这个的话是不用确定性。如果要按从你的考虑上，对这个考虑，那你这个是有所支配。好，看到那个路边的可以把这样子。对，为什么提升？你现在什么经历？所以为什么就直接？那个absolutely convergence to halfway. 那 ratio test 的定义的话是这个小于这个绝对值嘛，因为它的动物非常的所以说，那我这个考虑是要去查那个必须出现在那个对方看肯定100分。对吧？而且开始找每天都要啊。对对啊。就再说太多。
现在你可以讲，先开始。
Ready? Ready? Okay. So next part is the first cosine series as far as sine series. So what does this mean? So let's say we only define from 0 to L. Okay, just now we have function from minus L to L. Okay, and then we extend it. But now let's say we only have half of it, 0 to L. Okay, 0 to L. So maybe you will think that what's the difference between 0 to L and minus L to L? Okay, right? Because you can easily change 0 to L to some maybe minus M to M, right? Okay, you just move it. Okay, so the point they want to focus here is, let's say we only have half of it. Okay, we want to complete to the other half. So what we do? Okay, let's say we have a function and then we want to complete the other half of it. Okay, so what do I mean by that? Okay, it's okay you don't understand, but let's see what to do. In this case, we may choose to extend the function to be even, which we call the Fourier cosine series, or odd, the Fourier sine series periodic function of period 2L. Okay, so let's say you only got 0 to L, only half of it. So you complete to a full period 2L. And then depend on what you want, what kind of completion you want. You want even or odd. Okay. So I haven't tell you how to do it, but we are going to do it. So for example, let's give an example here. So consider this function here. Okay. So this is a piecewise continuous function. So piecewise continuous. Is it continuous? How to check this piecewise function is continuous or not? Anyone have any idea? How to check? There's really one point to check. Which is the one point? Which one? S equal to 1, right? Because that's the connection. Because apart from the connection, they are all continuous. It's just X or just linear graph. But when they connect, make sure they connect at when the limit equal. Okay. So fx equal to x is the usual linear graph. So when x equals to 1, it stops at 1. Okay. How about 2 minus x? Okay. Minus x is the other direction, right? So now you want to shift it out by 2. Okay. So you shift it out by 2. Where is the y-intercept? Where's the y-intercept for x minus 2 minus x? Where's the y-intercept for 2 minus x? It is 2. Okay. So how about the x-intercept for 2 minus x? What's the x-intercept? Also 2. Okay, also 2. So you draw a line across 0, 2, and 2, 0. Okay, but you want to cut it away from x less than 1 and greater than 2. So you cut the rest. Cut the rest. Okay. And here. Oh, even though I remove, it still count as a one line. So maybe just fill it in. Okay. So this is our function. So we want to complete it to even or odd function. Okay. So we need to extend over 2L. So maybe we need to extend over this part here. So up to minus 2. Okay, how do we extend it? Okay, so let's see how do we extend it. So one way you can extend it is this way. Okay, so you just repeat these mountain. Okay, just repeat the mountain graph. Okay, so this is the even extension. Is this even? Even, right? Okay, because if you p an x and a minus x here, they are the same point. Okay, so how to make it odd? Okay, how to make it odd? So you can consider this kind of extension where you take the f minus x to be negative. Okay, because you need to satisfy fx equals to minus f minus x. Okay, so it goes down on the other half. Okay, so this is the odd extension. This is an odd extension you can consider. Okay, so really we can find this extension. So let's see how to find this. So let's find the two half range series expansion. Okay, so meaning the odd, these are the odd extension and the let me write down. So this is the odd extension and the even extension. Okay, let's see how to do it. So how we do it? Just now it says that when it is odd, right, there's only sine part popping out. When it is even, there's only cos part popping out. Okay, so we just need to find the coefficient of an and bn. Okay? Let's say we want to find the Fourier series, Fourier cosine series. Okay, so now we start with even part. Okay, so for even part, what do we need to find? We need to find a0 and a0, an. Okay, so from just now experience, we know that we need to integrate from 0 to L. Okay, fx for this constant. And then for an, we integrate from 0 to L, fx time cos n pi x over L. Okay. So what's our L in this case? So our function is defined from 0 to 2 and then extend. So our f is defined from 0 to 2. Okay, so in this case, our L is 2. Okay, make sense? Okay, so we just do the sub our function and L int. Okay. So can we write the function out or not? Yeah. So this is a piecewise function. So if we want to integrate the piecewise function, we need to do it piecewise. So we need to break our integral into 0 to 1 and 1 to 2. Okay. Because they behave differently. So from 0 to 1, you have x. From 1 to 2, you have 2 minus x. Okay. So if you integrate these, I guess you get 1. You get 1. Okay. Okay, next. I mean, you can check my answer. You can check this. Okay. Next, what do we do? We also do the same thing. Okay, so we do the same thing, but this time we have extra coefficient. Okay, so 0 to 1, x cos. Okay, here is pi over 2. Okay, dx plus, okay, because it's just 1, right? So we just split it up. So 1 to 2. Maybe we just put this big bracket first. And then 2 minus x cos and pi x over 2 dx. Okay. I think there's no issue with the substitution this time, hopefully. So what you do next? I think there's similar stuff coming out again. You need to use by part. Okay, use by part. But this time I think you just need to by part once. There's only one x. Okay, so if you go around with this long step, what you get is also a long answer. So you can check this out. So this is also a long answer. You will get 4 over n squared pi squared 2 cos n pi over 2 minus 1 minus 1 to the power n. So they are all stubborn terms. They don't want to go away. Okay, so you get this long coefficient. So in this case, our Bn is 0, right? Because it's even part. So our FF will come out to be 1 over 2 plus the sum of n equals 1 to infinity. And then this huge coefficient, the really huge coefficient, in front of every cosine wave. Okay. Here. Okay. So it turns out that the curve we draw just now is actually this described by this Fourier series. Okay. So if you like, you can use the online what is it called again? Fourier series grapher to plot it. Fourier series grapher. Okay, plot it. Okay, so similarly, you can do a similar step to find the Fourier sine series. Okay, just that you need to replace every cos by sine, and then you should check that you got this. Hopefully, it's correct. You can check that whether you get this or not at home. Okay. So you can see that kind of fascinating here. So you have a power of sine. Okay. Here also have power of cos. Okay. Yeah. Any question up to now? Any question? No. Yeah. Any question? No. Okay. Next part is this Fourier transform. So this is also, I mean, the technique is similar to how you do Fourier series, okay? But we integrate over different stuff now. So the idea behind Fourier transform is you transform, okay, let me highlight. So you transform a function with respect to time to a function with respect to frequency, okay? So in this schematic picture here is, just now we have, remember we take linear combination of sine and cosine wave, okay? And then when we combine, we'll get some periodic curve coming up, okay? So this is a function against time, okay? But when we do Fourier transform, we project the curve on a different plane, okay? We project the curve, the wave on the other side, okay? Where we get a curve, a function against frequency. Okay? Do you get it? Get it? Well, you can, while sleeping, you can get it. Very good. Okay, still listening. Good, good, good. Okay, so yeah, so we project on the other curve. So I mean, project on the other plane. So you might wonder how we project on the other plane. Okay, so how we project on the other plane, right? So let's see how we project on the other plane. So I still don't want to tell you yet. So what's the Fourier transform? Fourier transform is closely related to complex Fourier series. So how to relate to another plane have to have something to do with complex number. Okay, so there's some hint here. I still don't want to tell you yet. So let's see. I think next we will see it. So next we will see it. So given the function f, okay, we don't need to start with a periodic function. We just need to start function on minus L to L and then extend it to a periodic function. Okay, just now we already seen it before. And the complex Fourier series is defined by the following. Okay. Instead of cos over cos and sine, this is over cos and I sine, right? Is it? Okay, wait. So do you guys know this identity? Divide by 2, is it? To divide by 2. No need? No need. Okay. This identity here. Okay. So instead of cosine and sine, we split it into cosine and I times sine. Okay. So we project it to other plane. Okay, complex plane. Okay. So compactly they combine. Sorry. So compactly they combine these two coefficients here. Okay. Yeah. So how to connect this complex Fourier series with the usual one? So you can do this change of variable. Okay, you can do change of variable. So you might wonder where the other half gone, right? Because in Fourier series we have an and bn, but in this complex series we only have cn. Okay, so where the other half go? So in fact, they break into cn and cn minus 1. Okay, cn from one group, cn minus 1 from the other group. Okay. Maybe so far doesn't make sense, but these are the facts. We will see example soon. Okay, so what's next? So let's see. Should we see it? Yeah, I think we should see it. So let's do it. So let's see why is this true. Okay, so we got this identity here. Let's write down e to the minus x equals to cos x plus I sine x. And then e minus ex again is what? So if we substitute minus x to cos x, we get x again because cos is even. So since sine is even, so we will get minus sine x. Okay. So alright, since cos x is even and sine x is odd. Okay. Do you guys know the story of this? Or I mean, in particular, e to the I pi equals to minus 1. I see one nodding head. I think this is one of the genius equation that has been written down. I think by Gauss. Gauss, is it Gauss? No. Euler, okay, Euler. Euler equation. Yeah, Euler equation, yeah. So you see on the right, so on the right hand side, right, is a real number. On the left hand side, right, they are complex or irrational. So why these things put together and then become a real number? So this is the special part of this equation. Okay. Okay. Anyway, next. Keep going. So keep going. So okay. So previously we have cos and sine, right? So let's see how we express cos and sine in terms of exponential function. So cos x is equal to what? Okay. So we can rearrange this term to get cos x equals to e to the power ix plus e to the power minus ix over 2. And sine x also can get e to the power x minus e to the power minus I theta over 2i. Okay. Right. So remember what do we have just now? Okay, a Fourier series of x. What's the formula? Yeah. Yeah, because the dot here theta, so I forget to change. Okay, thank you. So let me put the original function back first. So an times cos n pi x over L plus sum of n equals to 1 to b and b. Sine n pi x over. Right. Okay. So let's sub these things in. Of this the whole thing here. Copy, paste. Okay, so but x become n pi over lx, so we need to add in the corresponding term. So we get n pi over l, n pi over l, sum of n equals 1 to infinity bm times sub x equals to n pi over l, n pi over l. Okay, let me see. So here x left out already, so put it back. Okay, so what's next? Can we combine terms? Let's see. So what's next? So maybe we can combine terms. What to do? What to do? So how to combine these terms? So we combine correspond to e to the ix n pi over l and correspond to e to the power minus ix n pi over l. Okay, so we split into these two. So an over 2 plus bn over 2i, and then plus an over 2 minus bn over 2i e to the minus I n pi over lx. Okay? Okay? Does everyone agree? Or no, sorry. Does everyone agree? Agree? Okay? So you can see that now we split into the part with n and minus n. Okay, just now we mentioned that our Cn split into n and minus n. Okay, so this is where it came from. So let me label this guy. What do we have? So for this part, we have the C0 part. This part, we have the Cn part. And in this part, have the C minus n part. Okay. So Cn is equal to 2n over 2 plus bn over 2i, which is equal to an minus I bn over 2, and then C minus n is equal to an over 2 minus bn over 2i equals to an I bn over 2. Okay, so we have this. this connection here. Hey, can I ask you guys a question? So do you guys did pre-read before you came to the class? No? Pre-read. I put out the previous year note. Did you read it before you come to the class? No? Yes, some yes, some no. Okay, I suggest you read it. Okay. I mean, I know you don't need to understand what it says, but at least you know what will be coming up soon. Okay, so that you will not as blur. Okay. So you need to read like what kind of object will come up first. You need to understand fully, but you can understand it, but not necessarily you need to understand it fully, so that you won't come in as blur. Okay. Otherwise, you will definitely blur. Okay. So please read it. I paused it previous year, not right. So please read it before you can. Read about few section. I think you guys, I mean, we know, I mean, how we progress, right? So you just read few section ahead. Okay. Yeah. Before coming. Yeah. Okay. So does everyone agree that we got the same result here? Okay. 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 If you want, you also can verify yourself at home. Derive it yourself. If you like. Okay. So next. So what's Fourier series? So Fourier series is defined as the integral from minus infinity to infinity of ft multiplied by e to the I omega t. Okay, so we put an omega there to absorb all these constant. Okay. After we define this Fourier series, right, we also can define inverse Fourier series. Okay. Instead of multiplied by e to the minus I omega t, we multiply by e to the power I omega t. Okay, we remove the minus. And then divided by 1 over 2 pi. Because you can check that actually if you do this, so if you do Fourier transform on the function and then do the inverse, you will get the original function back. That's why I call it the inverse. Okay, so if you are interested, you can short it. We will just see how to do Fourier transform. Okay, so there's two examples here. Find the Fourier transform of the following function. So what's ht here? Actually, ht haven't defined yet. So let's define ht. So ht is the heavy side function, okay, or the unit step function. So what does this mean? So this means that after t, it is 1. Before t, it is 0. So this is called the heavy side function. Or the unit step function. So how does this look like? So it's split between t equals to 1. Okay. So when t is greater or equal to 0, it is 1. Okay. When it is less than 0, it is just 0. Let's make it Is there a real person? Okay. Good. Wake everyone up. Okay. Okay. So yeah. So we have this heaviside function. Okay. So if we replace with minus t, okay, imagine what happened when replaced by minus t. Can you imagine what happened if I replace with minus t? Substitute minus t. So how does this domain change? First one will change to what? 10, yeah, t less than equal to 0. And then the other will become t greater than 0. Okay. So they swap, not just swap, but so it will be like 1 first and then diminish. Okay. So, instead of starting with 0, you start with 1 and then you diminish. Yep. Okay, so we define everything here. So we want to use Fourier transform. Okay, so for now, for purpose of this course, right, you just need to know how to do Fourier series and Fourier transform. So you just need to know how to use the formula. So what's the formula? Let's recall the formula. So let's do the first one. F of F1t. So Fourier transform, do we use a different notation? Seems like not far different from what we have. Did we? Oh no. Okay, so we need to use the set bracket. Okay, so this is the Fourier transform. Okay. Yeah, let's do Fourier transform. Fourier series, remember, is f with a little small f. Okay, so this is a Fourier transform. Oh, sorry, this is a Fourier series. Fourier series. And then this is the Fourier transform. And make sure you differentiate the notation. So what's the Fourier transform? Okay, it's okay you don't remember, but I will write out. So you integrate from 0 infinity to infinity. F1t, okay, multiplied by what? Okay, now we don't want to do cosine anymore. So we combine cosine, okay, using the complex coefficient. So we have an e to the minus iw y omega t, okay, dt. All right. So if you see this integral from minus infinity to infinity, you should be worried. You should be worried. The domain is infinite, right? So typically you will get some infinite stuff if your function doesn't behave well. Okay. So this question here set out the question very nice. They Q off anything below 0. Okay. And then above 0, what is it? It is e to the minus at. E to the minus at. Anyone know how to plot it? It's a decreasing function. Okay. So it's decreasing. So you need to decrease as fast as possible so that you can get a finite sum. Okay, it turns out that this decrease fast enough, you can get some finite sum. So let's see what we get. So this is a piecewise function, right? So piecewise function, of course, you need to check whether it's continuous or not. But let's do it. It is continuous, so we integrate from 0 to infinity. Okay, anything below 0 is just 0. So I have to do this, e to the minus at times e to the minus omega t dt. Okay, does everyone agree we want to do this integration? Integral, I mean. Okay. Okay. So let's continue. So what to do? What to do? We just combine the power of the interval. Okay, so what's this? What's this like? This. So you need to kind of split this interval into the, what do you call the Okay. The improper integral. Yes, we need to do an improper. Because you cannot just substitute infinite, right? Infinity. So you need to do the improper integral. So I think integrate E is kind of easy. So differentiate or integrate E is if exponential function is just the exponential function divided by the power. I mean, using the chain rule. Then you evaluate this. Okay, you need to evaluate this. So what do you get? E to the minus over A plus I omega plus, sorry, minus, okay, minus minus become plus, so plus 1 over A plus I omega. Okay, so what's this? This is just 1 plus A plus I omega because these terms go to 0 under the limit. Okay, so what do we have? So let's summarize what do we have. So the Fourier transform of this graph become a function in T. Well, function in T. So did you realize that the left, the right, yeah, the right hand side don't have T. So it actually is a constant function. Yeah, it's a constant function. Okay. Yeah. Okay. So you can do similar stuff on B, and then you can check that it is actually 1 minus 1 over A minus I omega. Become a constant function. Okay. Yeah. Any question? Any question? Yeah. So you just plug in the right formula and then do the integral. How about this? Say, what's this? Huh? So this, let's do Fourier transform on this function. So this function is defined everywhere. Okay. This function is defined everywhere. And it is 1 when it is minus A to A. Okay. They call it a pause function. Okay. So what to do? So we do the same thing. Let's we do the same thing. E. Bring the formula up. Equals to from minus infinity to infinity of ft times e to the power minus I omega t dt. Okay. So how to integrate from negative infinity to infinity? The question Q the part from less than minus a and greater than a. Okay, so you need to just integrate from minus a to a, right? Okay, so when f is equal, when t is equal to minus a to a, ft equals to 1. Okay, this thing I think a bit easier because just finitely, definitely integral, definite integral. So what do we get? So we will get e to the I omega a over e, sorry, I omega and then evaluated from -a to a, which is what? Which is what? So which is e to the I omega a minus e to the minus I omega a over I omega. Okay. So what's this? What's this? What is this? Okay. So you can see that EIX and E minus X combined again, right? Remember just now we have some identity. What identity do we have? We have these two identities here. Okay. So we can make full use of this identity to write into a simpler form. And use these two to write into a simpler form. Okay, so we have a minus version. So we should get some sign out of it. So, but we need 2i to create this sign. Okay, so we just multiply and divided by 2. So we do a trick here. So let's do a trick. Do a trick equals to 2 over omega e to the I omega a minus e to the minus I omega a over 2i. Okay. So in this case, we found that the Fourier series is actually equals to 2 over omega times sine of a omega. Okay. So what's this? So what's this? So there's a picture here. There's a picture here. So actually, you start from this curve here. So let me zoom in. So you start from this curve, okay, and then what we found after Fourier transform is another curve from the other direction. Fourier transform. Okay, so the theorem says you also can start from the right-hand side and then go back to the left-hand side. This one is the inverse. Okay. Okay, so yeah, that's all for that one. How about this one? Okay. Wow, this one they didn't do anything to the sorry. So, okay. So for the next example, you can see that this is a decreasing function, but they didn't try to reduce the domain. So this question here, you need to rely on the fact this is something to do with probability, which I have no idea. So you need to rely on this fact that if you integrate this this whole thing here, get 1. There's a name for this. This is a total probability of n of mu sigma square distribution. Did you guys do probability or not this semester? Have you guys met some distribution yet? Not yet. Maybe you will see this integral soon in your probability class. Okay, so yeah. So if you try to find this Fourier transform, right? I think you will go from this blue line here to this red line. Okay. You can try and do it, and then in the middle of the step, you sure will use this identity. Okay. Maybe just quickly go over two property, and then maybe we'll stop there. So there are two property for this Fourier transform. Okay. First of all is the linearity. So if you want to transform a linear combination of two function, okay, then it is just the scalar multiplied by the Fourier transform of the first function plus or minus, depend on C2, times the F Fourier transform of F2. Okay. The second one is the symmetry. Okay. So if you trying to, okay, so what's this F hat here? So we should define F hat first. So what is F hat? So F hat is actually defined by the Fourier transform of another function. Okay, so that means if you transform again, what happened? Okay, so if you transform the second time, okay, what you get is 2 pi of the original function evaluated at minus omega. Okay, so somehow you go back to the original function, but kind of scale. Okay, scale and reflected. Yeah, scale and reflected. Okay, when you do twice. Okay, maybe we don't want to do example today. Maybe just give you an idea and then we'll stop here. And then after this one, I think will be more interesting. Okay, we will play around with geometry and polynomial. Okay, I think series is a bit dry. A lot of tests, a lot of formula. Yeah. After this, we will draw more diagram and then, yeah, more diagram, more geometry and algebra. Okay. Yeah. Before we end, any question? Any question? And did you guys start doing the tutorial question, review question or not? Review question I haven't put yet, right? Did I put? I think I put, right? Chapter 11. Yeah. So if you like, you can do those as quiz, meaning don't look at the example and don't look at the solution first. You do first, spend time do first, and then you check with the solution yourself. If you cannot do the solution, cannot do the assignment, and cannot do the exercises, or you stuck at one place, you just screenshot or what, send to me, email or message. Okay. And then if I think that it's worth to do in front of you, then we will discuss it together. Okay. Please do it yourself. I will check your work. Okay. You need to be independent. Okay. 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 Please do it. Don't wait until last minute. I think you won't have time. So see you this Friday online, is it? Friday online, 10 o'clock. Okay. Sure. See you online. Tell your friend that didn't come today. Okay. Tell your friend. Hey. Yeah.
Go to